Alright, so calculus with parametric curves. So let's start off with the theorem. It says if f and g are differentiable functions of t, and x is equal to f of t and y is equal to g of t, then dy dx is equal to dy dt divided by dx dt, as long as dx dt is not equal to 0. Well, let's see why that's the case. So if we start by using the chain rule, on y equals g of t, we want to find dy dx. So if I take d dx of y, that's going to be the same as d dx of g of t. Well, on the left-hand side, d dx of y is just going to be dy dx. But here's where we need the chain rule. We're differentiating g, which is a function of t, with respect to x. So then t is going to be some function of x in this case. So then we're going to have dg dt, dx, dg dx times dx dt. And that's by our chain rule. We're just differentiating through our intermediate variable x. And that gives us the following equation. If I solve this for I wrote this down wrong. I'm differentiating with respect to t, not with respect to x. I'm like, that is not working at all. So if we do this, but we treat t as a function of x, we're going to get dy dt is equal to dy dx times dx dt. And that's just our chain rule from Calculus 1. We differentiate through our intermediate variable, and if we checked, our dx's reduce out and we'd get dy dt. Well, the derivative that we are trying to find is actually this piece right here. So if I have dy dt is equal to dy dx times dx dt, I can solve for dy dx by dividing by dx dt. Finally, putting all of that together, I get dy dx is equal to dy dt divided by dx dt, or g prime of t divided by f prime of t. So this is exactly how we are going to differentiate y with respect to x. We have to use the fact that t, as we were doing last time when we eliminated the parameter, is actually can be thought of as a function of x. So then when we differentiate through with the chain rule, we end up with the following. So one thing we have to be careful with, and that is the warning that comes next. Is that our second derivative is not going to be d2y dt squared over d2x dt squared. It is d2y dx squared is d dt dy dx over dx dt. So why is that going to be the case? Well, because we'd have to do exactly the same thing again. So if we have dy dt, and we want to take its derivative, and we take its derivative with respect to t, and differentiate through x, we're going to have pretty much the same thing. To simplify this, instead of writing dy dt, I'm going to write it as y prime. Or sorry, dy dx. I'm going to write it as y prime. We would then have dy prime dx times dx dt. So then, solving for this, once again, we would have dy prime dt is equal to dy prime dx times dx dt. So then solving for this guy, once again, the derivative of y prime with respect to x is going to be the second derivative. So that's d2y dx squared is going to be equal to this, which is just going to be d dt of dy dt, because it's the derivative with respect to time, and then dx dt. So we divide once again by dx dt, and divide by dx dt, finally getting d2y dx squared is equal to d dt dy dt divided by dx dt, which is what we claimed above. So be careful, there is a false friend here when we're taking derivatives. If we want the second derivative, that's our formula. If we want the first derivative, that is our formula. They are both consequences of the chain rule and treating t as using the intermediate variable x as we differentiate through. All right. So let's go ahead and use that to work on example 1. So a curve is defined by x equals t squared and y equals t cubed minus 3t. Show that the curve has two tangents at the point 3, 0. B, find the points on the curve where the tangent is horizontal or vertical. C, determine where the curve is concave up or concave down. And D, sketch the curve. Okay, so we want to find its tangents at the point 3, 0. So the first thing we need to do is find out for what value of the parameter does x equal 3 and y equal to 0, right? Okay. Well, that would be, we need x to be 0, so that would give us the equation 0 is equal to t squared. Nope, 0, I did that wrong. X should be 3. So t squared should be 3, And then when is y equal to 0? That would be 0 equals t cubed minus 3t. So we solve each of these equations. For our first one, we get t equals plus or minus the square root of 3. So our two possibilities are t equals the negative square root of 3 or t equals the positive square root of 3. We do the same thing with our t value here. So we factor out a t, and that gives us t squared minus 3. And that gives us t equals 0 or t squared minus 3 equals 0. We solve for t, and we get t squared equals 3. Oh, that's the same equation we had over here. So we're going to get t equals negative root 3 or t equals positive root 3. So this one doesn't have a match with the x's, so it's not going to be at the right place. So the values of our parameter are going to be negative root 3 and positive root 3. So then we need to show that it has two different tangent lines. So to find the tangent line, or the slope at that point, we need to find the derivative. So to find dy dx, we need to calculate dy dt over dx dt. So our dy dt is going to be 3 t squared minus 3. And our dx dt, the derivative of t squared, is going to be 2t. So then at each of those parameters, so dy dx evaluated at t equals negative root 3 is 3 times the negative square root of 3 squared minus 3 all over 2 times the negative square root of 3, which gives us negative square root of 3 squared is 3. 3 times 3 is 9. 9 take away 3 is 6 over negative 2 square roots of 3. So that's going to be the slope of our first one. And then we're going to get pretty much the same thing, but with the opposite sign. When we do our other one, square root of 3 squared minus 3 all over 2 times the square root of 3. This time we get 6 over 2 square roots of 3. So this one is negative 3 over the square root of 3, or negative 3 root 3 over 3. And then our 3's reduce out, so negative square root of 3. We do some similar manipulation over here. Rationalize 3 root 3 over 3. Our 3's reduce out, and we get the positive square root of 3. So our derivative at the point and our point was 3, 0 with t equal to the negative square root of 3 is negative root 3. And the slope at 3, 0 with t equal to the positive square root of 3 is, our slope is positive square root of 3. So at that point, we have two different slopes depending on which time we visit that place. So remember, with parametric curves, we can be in the same place at different times. So on the first pass through or the second pass through, we're going to have different slopes. Okay, part B asks, find the points on the curve where the tangent line is horizontal or vertical. Well, x tells us about horizontal motion. So it tells us about moving right and left. So if I'm not moving right or left at all, that means I would be going straight up or down. So similarly, to find horizontal tangents, that means that my y value is not going to be changing. So here, for horizontals, I would want dy dt equals 0. For verticals, we want dx dt to be equal to 0. So we take our derivative once again. So dy dt, where y is t cubed minus 3t, so dy dt is going to be 3t squared, take away 3. And our dx dt, taking our derivative with respect to x, is going to give us 2t. So we solve each of these equal to 0 to find our respective horizontal and vertical tangents. So we did this before, so add 3, and get 3t squared equals 3. Divide by 3, divide by 3. So t squared is equal to 1. Taking our square root, t equals plus or minus 1. So our graph is going to have a horizontal tangent when the parameter is positive 1 or negative 1. Similarly here, we divide by 2, divide by 2. We'll have a vertical tangent when t is equal to 0. So to find these points, we're going to use our original function. So x is t squared and y is t cubed minus 3t. So x of negative 1 is going to be negative 1 squared, which is 1. Y of negative 1 is going to be negative 1 cubed minus 3 times negative 1, which is negative 1 plus 3, which is 2. So it's going to be the point 1, 2. And if we rinse and repeat with our positive value of t, so x equals 1, we have 1 squared, which is still 1. And y of 1 is going to be 1 cubed minus 3 times 1. And 1 minus 3 is negative 2. So we're going to have another horizontal tangent at 1, negative 2. We do our vertical. We have x equals to 0 squared and y equals to 0 cubed minus 3 times 0. So x is 0 and y is 0. So we end up with 0, 0. So our vertical tangents are at the point 1, 2 and 1, negative 2. Our horizontal tangents are at 0, 0. So part C wants us to determine the concavity of the graph. Well, we have our derivative that we calculated back here in part 1. So we have dy dx is equal to 3t squared minus 3 over 2t. So to find concavity, we need the second derivative. So is determined by the second derivative So our formula for finding the second derivative was d2y dx squared is d dt of dy dx divided by dx dt. So before we dive right into this formula, let's simplify our dy dx a little bit. That's this guy. Would be the same as 3t squared over 2t minus 3 over 2t. So that's going to be the same as 3 halves t minus 3 over 2 times 1 over t. And we can note that 1 over t is the same as t to the negative 1. So then d dt of dy dx is going to be, well, the derivative of 3 halves t is just going to be 3 over 2 minus 3 over 2 times the derivative of t to the negative 1 is going to be negative 1 t to the negative 2 over dx dt. Well, x is t squared, so dx dt is going to be 2t once again. So cleaning this up a little bit, we have 3 over 2, minus minus makes it plus, 3 over 2, and then t to the negative 2 is 1 over t squared times 2t. All right, let's keep cleaning that thing up. So in the numerator, we have 3 plus, getting our common denominator here, we would need a t squared and a t squared. So that's going to be 3t squared plus 3 over 2t squared divided by 2t over 1. And if I have a fraction divided by a fraction, I multiply by the reciprocal. And let's factor a little bit. So 3t squared plus 1 all over 2t squared times 1 over 2t. Finally, our second derivative, d2y dx squared, is going to be equal to 3 times t squared plus 1 all over 2 times 2 is 4, t cubed. So now to find our concavity, we need to find when this is 0 or undefined. So our numerator, t squared plus 1, this is never 0. And this is undefined at t equals 0. So if we test t equals 0, we need to pick a sample point on either side of 0. So for no reason whatsoever, other than it's a simple number, let's pick negative 1. If I put negative 1 in, I get 3 times negative 1 squared plus 1 all over 4 times negative 1 cubed. So that's 3 times 2 all over 4 times negative 1, which is 6 over negative 4, which is negative 3 halves. So that means this side is negative. And then we test something on the other side. So let's test positive 1. And we're going to get pretty much the same thing. So 3 times 1 squared plus 1 all over 4 times 1 cubed, which is still 3 times 2 over 4 times 1, all positive this time, so 6 over 4, which is 3 halves. So over here it's positive. So then, from negative infinity to 0, our graph is going to be sad, right? So that means it's concave down. And then from 0 to positive infinity, we had positive, so our graph was happy, and it's going to be concave up. And that just came from our number line by doing our test points on either side, right? So concave down from negative infinity to 0, and it's going to be concave up from, I wrote those backwards, 0 to infinity. All right, and there we go. So I've got to be a little careful, though. Which variable are we talking about here? When I say negative infinity to 0, I'm not talking about x's. What am I talking about? T's, right? So this is t less than 0, and this is t greater than 0, right? Because our input variables are t's, not x's and y's. X's and y's are our outputs. All right, so let's go ahead and sketch our graph, and then we'll do so with our calculator and see what it looks like. So what did we figure out amongst all of our doings? So in part A, we discovered that our graph is going to go through the point 3, 0 twice and have 2 different tangent lines. So in part B, we found out that our graph had 2 vertical tangents and 1 horizontal tangent. So our graph has vertical tangents. I did those backwards. Well, that's twice today. We solve for them correctly, but this one goes here. So what happened is I just wrote down the wrong thing. We solved the horizontal tangents were here, and we got 1, 2, and 1, negative 2, but then I wrote vertical in the wrong place. So I just wrote these 2 things in the wrong place. We did all the math correct. I just wrote it down wrong. So our horizontal tangents occur at 1, 2, and 1, negative 2. So 1, 2, and 1, negative 2. Our graph is going to have horizontal tangent lines. At the point 0, 0, we are going to have a vertical tangent line. We know our graph is going to go through that point twice, once with a slope of positive square root of 3 and once with a slope of negative square root of 3. So we could pick a few points to help us draw this, but we know that our graph's going to have to look something like this. It's going to go through this point, have a horizontal tangent, come down. It's going to do the same thing, horizontal tangent, turn around, and go back up. It's a terrible by hand sketch, but let's see what our calculator thinks. So first, if your calculator, for whatever reason, is not in parametric mode, let's go ahead and put it in. And then we put in our x in this case, which is t squared. And we put in our y in this case, which is t cubed minus 3t. And we graph. Looks to me like we only got this piece of our graph. Why is that? Well, let's go ahead and change our window and see why. Oh, t min. So let's at least go to negative 2 pi and see what we get. So negative 2 pi. And let's change our x min is 0, x max on this graph is 4. And let's make our y min and y max 4 and 4 as well. If we do that, try that again. Y equals, we have t squared and t cubed minus 3t. Window, let's go t min is negative 2 pi. X min, negative 4, 4, that's fine. Negative 4, 4. Let me press graph. There we go. And we use our calculator to graph in parametric mode, and our sketch isn't half bad, right? So we see we get the same tangents. So we have a tangent horizontal here, here, our vertical, and our graph has the two tangent lines, each with the slope as advertised at that point, right? So our parametric curves can do things that other curves couldn't. This curve crossed itself. For traditional functions, that's not allowed, right? You can't equal the same thing at two different points. But it turns out that we need this to do a lot of things. All right. Now your turn. We'll have to finish this up next time because we're running out of time, but I do want to show you the picture before we leave. So if I switch my mode back to function mode and go y equals and then graph this thing, sine x over 2. If I graph that, zoom 6. Actually, we're out of time. We'll look at the picture next time. So, all right, so to finish this integral, we just need to make sure that we can simplify this absolute value of sine theta over 2. So if we were to graph this thing, we have the sine theta over 2, and let's go ahead and change our window. We want to go from 0 to 2 pi. And yeah, everything else should be okay. So we get something that looks like this, and we see on 0 to 2 pi, it's always positive, so we don't have to worry about the absolute values and have it changing sign. If it would have intersected the x-axis and had negative area, we would have had to break it up into multiple different parts. But we want to take note that this is always greater than or equal to 0 on 0 to 2 pi. So then sine theta over 2 is going to be equal to the absolute value of sine theta over 2 on that same interval. So now we just need to integrate 2r times the integral from 0 to 2 pi of sine theta over 2 d theta. So our antiderivative of sine is negative cosine. So we have 2r times negative cosine, but then we have to divide by a half, so negative 2 cosine theta over 2, and then we're going to evaluate that from 0 to 2 pi. So this gives us negative 4r cosine theta over 2 evaluated from 0 to 2 pi, so negative 4r times putting in the 2 theta, or putting in 2 pi for theta gives us 2 pi over 2. So the cosine of pi is negative 1 minus putting in 0. The cosine of 0 is 1. So negative 1 take away 1 is negative 2. So we get negative 4r times negative 2, which is 8r. So the arc length of the cycloid over one cycle is 8 times the radius. So we want to show that the surface area of a sphere is 4 pi r squared by rotating the semicircle x equals r cosine t and y equals r sine t for 0 less than t less than pi around the x-axis. All right, so we want to use this. So we're going to have our integral from 0 to pi of 2 pi y, and our y is r sine t, times the square root of dx dt squared. So the derivative of r cosine t is going to be negative r sine t squared plus the derivative of y, the derivative of sine is cosine. It's going to be r cosine t squared dt. So simplifying, we get 2 pi r sine t. And inside our radical, we have r squared sine squared t plus r squared cosine squared t dt. So factoring out our r squared, we're left with sine squared t plus cosine squared t. And sine squared t plus cosine squared t by the Pythagorean theorem, or Pythagorean identity, is equal to 1. So 1 times r squared is just r squared, and the square root of r squared is r. So finally, after all that, we get 2 pi r squared sine t dt. So taking our antiderivative of sine, we're going to have 2 pi r squared, and the antiderivative of sine is negative cosine. We evaluate that from 0 to pi, which is pretty much what we just did. So 2 pi r squared times, I'll put the negative out in front. So then cosine of pi is negative 1 minus cosine of 0 is 1. It gives us, once again, negative 2. We get 4 pi r squared, which is what we wanted to show, that the surface area of a sphere is 4 pi r squared.